So now we're going to move on to our second coding assignment. In this assignment, you're going to implement 2D versions of the Fourier transform and inverse Fourier transform for applying them to images. Again, as before, you are provided with two Colab notebooks. One has the skeleton code and the other has the solution. After you go through the trouble of implementing these two functions, and it's not much trouble at all, as you will see, you will realize that they are unusable because they have a very high time complexity, m squared, n squared. So then I'll show you a better way to vectorize these functions and come up with a lower time complexity that actually makes your functions usable for images. This is still not as fast Fourier transforms, which have an mn log mn time complexity, but it's good enough for small images. I will implement the first function, the forward transform, for you in a vectorized fashion, and it'll be up to you to implement the inverse Fourier transform in a vectorized fashion. And finally, you will use these functions to visualize the magnitude spectrum of a cat image and then try to reconstruct the cat image from its Fourier transform. So let's get to it. Let's click on this link. So here's the Colab notebook. This is the formula for the forward Fourier transform in 2 dimensions. Again, fmn is the pixel intensity of each pixel. You have 2 separate omegas, the formulas for which are written here. You sum over all pixels, and that computes the Fourier index for a single UV index. And then you have to compute it for all indices. Before, when you did this in 1 dimension, you had one sum and one index k, and you had to create 2 loops. One would be to create, to sum over all samples, and the second was to populate the Fourier transform table for all the indices k. In this case, you'll end up with 4 loops as shown over here. The 2 inner loops will sum over all rows and columns, and then after you've done all that, you have computed only a single index UV. For example, if you're looking at a horizontal frequency of 5 and a vertical frequency of 10, after doing the double summation, you have computed the Fourier value for that specific frequency. But of course, we want to populate the Fourier table for all the frequencies in our image. So then you have to iterate over all u's and all v's, and that's what the 2 outer loops do. It's really quite simple. All you have to do is implement this formula in these 4 loops, and then there's a test cell that'll test your implementation against the CV2's discrete Fourier transform for 2-dimensional images. And then you do the same for the inverse discrete Fourier transform in 2 dimensions. Here's the formula. The only difference from before is that here the exponents are negative, and you normalize the double summation by dividing by the number of pixels. I'll let you implement that. There's a test cell to test your implementation. And again, because we have 4 loops of length m, n, m, n, the time complexity of these functions will be m squared, n squared, which is way too slow for images. So we need to do it in a better way. And there's a good vectorized way of doing this. It has a very simple formula, Wm times x. This is matrix multiplication by x, which is the image, multiplied by Wn. Wm and Wn are called basis matrices. And what they are is that for every u and m, that is for every row and row frequency, we populate an m by m table or matrix. And we do the same for every column and every column frequency. We populate an n by n table. And then once we have done that, we simply plug them into this formula and we do matrix multiplication by the image x. The forward transform I've done for you. This is a vectorized way of creating these basis matrices W sub m and W sub n. And then all you do is you do the matrix multiplication and you end up with your Fourier transform in a much more vectorized and faster way. And then you can use this to, the function you just created, to get a cat image and compute its Fourier transform f and plot it. Here's the cat, here's its Fourier transform, which is quite accurate. Then you will move on to implementing the inverse Fourier transform in a vectorized fashion. This is the formula for it. These are the two basis matrices, and it's quite simple for you to follow the same pattern to implement it here. And then once you have created your inverse Fourier transform, I want you to try to start with your Fourier transform f and then feed it to your inverse function and see if you can reconstruct the cat image. So you want to go back from here to here. The only thing you have to keep in mind is that your Fourier transform had a real component and an imaginary part, and you're only interested in the real component to plot the cat image, and you can extract the real component from your f by using the numpy's real function. Next, we'll do a short quiz that tests your knowledge of 1- and 2-dimensional Fourier transforms.